So it's 11 o'clock. Good morning, everybody. I welcome you to the online workshop Dynamic Beam Shaping. On the next slide, I have some organizational notes to everyone. Please mute your microphone and turn off your camera in order to minimize interferences. The second topic is the online workshop will be recorded and made available for all participants afterwards. In the case you have questions, which I hope, please use the chat function to ask questions. Patrick Herwig, actually, he is our expert for laser cutting. He will collect the questions, and then actually we will try actually to give some answers, but I'm asking you for some understanding that we will not be able actually to answer each single questions, because we have more or about 100 participants. So this is actually the audience. Actually, we have too many people here listening, which is a good thing, but we have to sort and select the questions, So you can access the chat by clicking the icon in the menu bar. What are we talking about this morning? We have part one of our program. So we will start actually with two presentations from Fraunhofer IWS. The first presentation is about the state of the art of laser welding with dynamic beam shaping based on conventional mirror optics. And this will be done by Dr. Dirk Dietrich. He works for Fraunhofer IWS, and he is the expert for laser welding applications. The next talk is a similar talk about the state-of-the-art technology when it comes to beam shaping for laser cutting. And Dr. Patrick Herwig, he is our expert for laser cutting, will give this presentation. And then the last presentation for part one, and now it's getting more interesting because it will be held by Dr. Eyal Schegel. He is CEO of Civan Advanced Technology, and he will talk about the latest achievements in material processing using dynamic beam shaping by means of a coherent beam combined OPA laser. In part two, actually, I will give an overview of the first results which we have received with the laser, which we have installed quite recently and which we have gotten from Civan. So we are very happy to have this laser here, and we have spent the first week since we have the laser with the beam characterization. And then actually by last week we have carried out the first bead on blade weldings. So we turned on the laser and we did the first time here in our lab where we processed mild steel. And then actually the next talks will be about the first projects actually, which we will start here very soon in the next time. The first project is on-fly laser welding beam shaping for laser metal deposition of crack-sensitive aluminum and titanium alloys. And this talk would be given by Dr. Elena Lopez. She works as well for Fraunhofer IWS, and she is an expert for additive manufacturing. The next presentation will be given by Mr. Eric Punzel from BBW Laser Technique. This project is about laser welding of hard-to-weld aluminum alloys with new coherent beam combined shaping technology. This project is a joint project between Civan and BBW Laser Technology. It's under the umbrella of the network Pulsate, and it will be supported by Fraunhofer IWS. And our lab will be, and the Civan laser which we have here at IWS will be used for this project as well. And actually, the last point is a few words and sentences about the opportunities which will be given to third parties to carry out experiments supported by Fraunhofer IWS and by Civan with this new laser. And then we have reserved, some minutes, for a discussion. So then actually for the next presentation, I would like to ask Dr. Dirk Dittrich to share his screen and to take over the microphone and the camera. Dirk, it's your turn.
Yeah. Thank you, Andreas, and welcome everybody to my presentation. I'm trying to upload the presentation, and I hope you are able to see it now. Andreas, is this visible?
Yes, it is.
Yeah, okay, perfect. So I will start here due to the time that we have. I will go through this presentation, and if there are some questions, it would be great if you would ask them later on in the chat so that we can answer them after the presentation. Okay, I hope it's still visible. Did I moved something? Okay.
No, it's not.
It's not?
No, it's not.
Okay. Then I'm trying it again. Okay. Yeah, now it should be again visible for you. So,
yes, it is.
The title is State of the Art Laser Beam Welding with Dynamic Beam Shaping. I shortened the title here a little bit, and I will refer to our experiments that we have done in the recent years. At the beginning, for motivation, I was trying to collect here some sentences for why beam shaping and what are the limitations that we have right now with the static laser beam welding technologies. If you use only a fixed optical path, you're really demanding on the machine of moving the laser beam around the part, and you have not really an opportunity to have a fast intensity modulation or even a fast beam control. And that makes processes slow and doesn't give us the opportunity, for example, to work with mixed materials, as you can see here for copper and aluminum, or for other cast steel components. And the only opportunity that you have right now to address different intensities or a different wavelength according to the surface of the material, for example, for copper welding, is to use other laser sources, like laser source that provides green or blue light or near infrared light, or to use specific optics and optic setups to change intensities and so on. And on the other side, we don't have really an opportunity to provide spatter-free processes. For example, if we are welding aluminum die-cast material, which is shown here, because you have not that many opportunities for process control. And therefore, I think it's a great goal right now to look for flexible processes and to increase process stability. Okay, here I would like to draw your attention to these three options of dynamic beam shaping that we have. On the one hand, we have galvanometer scanners. As simple movie shows here the functionality. The beam is guided by mirrors, And this is something that is already introduced in the industry and available for a lot of processes. A second variant would be using piezo-driven actors. Here you will see in this short overview movie how this works. And this is a topic to enable, for example, focal shift and to add the third component to these galvanometer scanners, which I will present a bit later on this presentation. And this is in a transition between industry, between research actually and industry. And we are actually working on this. And then the third category would be a MEM scanner, which are available, but for high power application, it's quite difficult to have them stable for continuous welding processes. So in that case, this is still a topic of research to develop these optical units. If we are talking about 2D beam oscillation with galvanometric driven mirrors, then we are using usually fine laser sources, for example, single mode fiber lasers with Gauss mode, and then we are oscillating a circle, for example, and overlaying them with the welding speed, and then we obtain, depending on frequency and welding speed, of course, different energy depositions. That could be a homogeneous one or an inhomogeneous one, and therefore we usually calculate this with a specific software tool before we are starting the welding process. Same would be the case for scanning figure in the shape of an 8, and here again using different frequencies or different amplitudes, then we can modulate the energy deposition, and as it is shown here. And so we have a lot of varieties to interact with the laser beam and the material. Here an experimental overview for 2D beam shaping with high frequency, and we used here a 5 kilowatt single mode fiber laser with a really small core diameter, and we obtain a focal diameter of about 33 micrometer. And we have used this for welding copper material, which is shown here. And you see on the left-hand side, we have a penetration depth variation between 0.4 millimeters and 3 millimeters. And these we do all in one setup, only by changing the laser parameters and as well amplitude and frequency of an oscillating laser beam. Therefore, we are using a circle like it is shown here in this small figure. And so we can have different penetration depth and high quality laser beam welding results, especially for these low penetration depth. And that the oscillation gives us an opportunity to obtain smooth surface appearance of the weld seam is shown here. And this won't be possible to do with a static laser beam. Therefore, you would be forced to have at least 2 or 3 optical setups to reach equal results, or maybe not even this homogeneous weld seam distribution, maybe with a lot of inhomogeneities at the surface. Coming now to the second point, to 3D beam shaping. Here I would like to give a short motivation. And what we are facing in our research work is that there is a need of a lot of individualized and flexible processes to extend process limits. And therefore, it's not only about the geometry that we are welding, it's also about the material combinations, mostly for mixed materials that I have already addressed, and to be able to have a 3D processing which is quite fast compared to standard welding approaches. And the third point would be here to have the opportunity by piezo-driven unit to shift the focal position, and that is done by changing the the plane level here of this piezo-driven element, and then you are able to shift the focus properly. Okay, and what allows us this, it is shown here. We have an optical path consisting of collimation shown here, and then the 3D piezo-driven actor here for shaping the Z modulation or for moving the Z axis, and then a 2D scanner for moving in X and Y direction the laser beam. And therefore, it is already shown here, if you have no opportunity for this 3D beam shape, then you would have the issue that if you place a sheet under 30 degrees in the under the optics, then you would have the opportunity to weld circle, but not a full penetration. And if you use the focus readjustment, then you have the opportunity to weld the circle with a constant penetration depth. And this is one example for 3D modulation. There are, of course, many more with regard to focus shift and so on. Yeah, and at the end, I would like to conclude shortly. I think what is possible right now is that we have a lot of processes where we actually actively stabilize the process by 2D beam oscillation. And this is also shown by some weldings for aluminum die-cast material, which is already in the industry. And therefore, we are using the 2D beam oscillation quite successfully with reduced spatter and smooth seam topology. And for this novel concept of 3D beam shaping by using piezo-driven actors, we are able to move the beam in all three spatial directions, and we have a large possibility. We have large possibilities to have different energy depositions on the part by these options. Yeah, and so we are able to have an active focal shift adjustment, and to do this for high power applications. And that opens us a wide range of new process parameters for laser beam welding processes. So at the end, I would like to give a short outlook to the presentation that Andreas Wetzig will give you a bit later regarding this CBC laser source, which we have here available. And yeah, the opportunities that we have with this laser source will be quite larger than the ones that we have, for example, with 2D beam shaping. And at the end, thanks for your attention. And if you have questions, feel free to ask them. Thank you. Andreas, you
Thank
have
you,
some.
Yeah. Thank you very much. Because in order to be, in the time frame actually, and because I don't see any questions in the chat function actually, I would like to ask Patrick Herwig to continue with his presentation about state of the art of fast beam oscillation in the case of laser cutting.
Thank you, Andreas. So I will share my screen too. And let's start, yeah. Okay, hopefully everybody's seeing it.
Yes, so, Patrick, I can see it.
I will talk about dynamic beam shaping in state of the art, and especially our approach, which we think what we can do with this new possibility of this new laser source. Instead of what Dirk has done, I will have a deeper look into the physics of the process instead of the system technology. So let's talk about the basics of laser cutting. So laser cutting seems to be very easy because it's used in industry since up to 40 years. But from the process side and from the physics side, it's quite complex. Yeah. So laser cutting is a multi-physics of different things. So the main things are first, of course, absorption of energy. The absorption depends on the material, but also on the wavelengths of the used laser. of the angle of incidence of the beam, the roughness of the surface temperature, and of course also of the energy distribution to the surface. So the absorption depth of laser radiation is a few nanometers. That means we also need a kind of energy transport to the volume of the process zone. And also this transport depends on the temperature gradient of the process zone, of the heat capacity of the material, and of course also of the heat conduction of the material. And if the material is molten, of course we have also to eject the material. And ejecting depends on the used nozzle, the pressure of the gas we are using, of the cut curve geometry we are achieving, and of course also on the temperature of the cut curve surface. So these are from my side these three important physics basements we have to consider. But the question is, what could be influenced by dynamic beam shaping? And if we look to these three bullet points, we see in every point there is something with a temperature distribution, and energy distribution. So what we can do with dynamic beam shaping is to influence the interaction time between laser beam and material, and we can also manage the number of repetitions of these interactions. So this is no magic, this is well known. All users of laser machine are doing a pulse mode if they want to achieve higher quality, but a pulse mode will reduce the output of the machine. So the approach of dynamic beam shaping is to not switch on and switch off the laser. It's the approach to distribute the energy in the process zone. So that this strategy works and it's no fairy tale, I will skip to a quite easy example. So this is a quite huge slide. What we can see here, I will shift to the laser pointer or several things. Yeah, and the sorry, I will add the laser pointer is this one. Okay. So on the picture here in the bottom, you can see a look through the laser cutting optics and an image of the heat distribution during the cut on the cut front. Yeah. And in this diagram, you see on the x-axis the time, and on the y, you can see the temperature measured in this process zone on the cut surface, on the cut front. And this is the result of the cut. You see there's a little bit of dross on it, but we also use quite low laser power, that means 3 kW, and we try to achieve a quite a good cut. So what we can see in the diagram, the energy or the temperature is in a quite small band, yeah, and it's every time about the melting temperature of the material. So please remind these parameters, we are not using dynamic beam shaping. Our focus diameter is 200 microns, and the process speed for this cut is half meter per minute. Please keep your eyes to the width of this cut curve. If you are using dynamic beam shaping, you are able to use a special focal position, a quite higher focal position, which allow us to achieve a smaller cut curve. Yeah, everybody knows if we are doing it by standard cutting, we will get a worse cutting quality, so we call it a plasma cut. But if we superpose this dynamic beam shaping, in this case, we are using a frequency of 300 Hertz and the amplitude of 300 micron, we can achieve a quite good quality. And if you look here, also in a quite high process speed. So we could increase the speed from 0.5 to nearly 1 meter per minute. What we can see in the diagram and also in this small image or video down, this is a pulsing of the surface temperature of the cutting front. So we can see we influenced by distributing the energy, also the surface temperature. And as you remember to my first slide, the energy or the temperature distribution will have an influence to the material transport. And even the cut quality is quite better than compared to the beginning. So these two slides, we can see there is a quite large impact if we are using dynamic beam shaping, and we could increase the quality. So dynamic beam shaping is a quite wide field. Yeah, we have a 2-axis scanner, which is possible to do it in X and Y, and we have a wide range of frequencies and amplitudes. So we can achieve quite different beam shapes. Yeah. So in this diagram, you see on the X side different beam shapes. So we try to name it like it look like a circle, a 8, or a horseshoe. Yeah. And we have also our standard state-of-the-art stationary beam. And I try to put into this diagram 2 different parameter sets. The gray one, this square, is for good quality, and the green one, the circle, is for maximum speed. And I put in, additional into the achieved cutting quality by the US mask tool system. That means A is the really good cut quality, and D is acceptable cut quality. You can see we have a wide range if you are using dynamic beam shaping to achieve different targets. And here you can see summarized a shaped beam with a nearly frost-free cut, a smooth roughness, and compare the unshaped beam. You can see the separation line and quite hard frost attachments. Please have in mind we are cutting here 12 millimeters and using only 3 kW of laser power. Okay, so what could we do with a current beam combining is now the question I try to answer. What we can do is we can reduce the interaction time between beam and material, and we can increase the number of repetitions. And to see the potential was quite possible, I make a small calculation. So you remember we are cutting this 12 millimeters by a spot diameter normally around 200 microns and a cut speed of 1 meter per minute. That means for a static beam, we have an interaction time between material and beam of 12 milliseconds. If we care about this dynamic beam shaping with this frequency of 300 hertz and 300 microns, it's a sinus function. We can also calculate the superposed speed of the moved beam. So the moved beam of dynamic beam shaping will be in a range of 100 meter per minute. That means we can reduce the local interaction time from 12 milliseconds down to 120 microseconds. And if we go to the next level, that means CBC. CBC should be able to modulate the beam in the range of 2 megahertz, and 2 megahertz means for us we have the possibility to reduce the interaction time down to 500 nanoseconds. So, but the question is, should it be useful? So I could not answer this question in detail. Therefore, we have to do some experiments which are scheduled also within the next months. But I can give you a picture of my view. And my view is, if we are looking to the pulsed laser applications, and then pulsed laser applications, we know if we reduce the pulse length or the interaction time between material and laser beam, we could increase the quality. Of course, I know that we are the important point is not the laser pulse, it's also the long break between the pulse, but it should give you an impression that we can influence the process by reducing the interaction time and increasing the number of repetitions. So I try to calculate what's possible. You see here this table, yeah. I try to calculate the interaction times, significant beam diameters. So 50 microns should be what be possible with the CBC laser. 200 micrometers is a common focus diameter for laser cutting. Yeah, and if we are talking about our current state of the art, that means using galvo scanner, we are able to operate maybe in this field, yeah, to be in the action time around 1 microsecond or even below. And if we use CBC, we can enlarge this region quite good, yeah. So okay, it's up to 5 megahertz, yeah, but we will be in this region to have an interaction time in the region of 1 nanosecond. And you see, we have a large adaptation of this functionality that we can use for our investigation in laser cutting. So maybe I'm still at the end of my presentation. I say thank you, and if you have any questions, so please feel free to ask.
Thank you, Patrick. I can't see any questions in the chat, but we are on track so far. But however, I would like to introduce our next speaker, and it's becoming, approaching the topic. I'm very happy to have Dr. Eyal Shekel here. He is CEO and founder of Civan Advanced Technologies, and he will talk about the latest achievements in the material processing using dynamic beam shaping lasers by Civan, and I think he will also explain actually the physics behind of this laser. Eyal, I'm looking forward to your presentation, and it's up to you.
Thank you very much. So can you see my presentation now? It's on the screen?
Yes, Eyal. It's perfect.
Great. Thank you. So I'm Eyal Shekel, like Andrea said, founder and CEO of Civan. And before I start, I just want to thank IWS team very, very much, not only for inviting here us today, but for the support they have been giving us for the last couple of years. We learned a lot about material processing, about laser material processing, about the interaction of laser with material, and about the dynamics of the process and the importance of the beam shaping and dynamic beam. We learned it from the IWS team, and really thank you very much for all the support over the years. So in my talk, I will talk about the core technology. I'll show a few examples from our application lab, different research that we're doing. I'll say a few words about the future things we want to do, and one slide of summary. So just one slide about Civan. What we do is we manufacture high power lasers based on a technology that's called coherent beam combining, which allows us to do the dynamic beam. As far as we know, we are the only company in the world with a commercial product of high power laser based on coherent beam combining. We have many patents. We are 180 employees today, and we started at 2008. Took us a few years to get to the first high power laser. In 2018, we started shipping our standard OPA6 laser to customers. And just a few months ago, we delivered our first 100 kilowatt OPA laser to a customer. So what is coherent beam combining? Coherent beam combining basically is the ability to take many lasers and combine them together to have one single mode output. And the way it works is we take some seed laser that can be even half a watt, and then we amplify it. Each one of these triangles is an optical amplifier. So we amplify it, we split it, we amplify again, we split again, and we amplify again. And this at the front line, each one of these amplifiers can provide up to 1 kilowatt of single mode output. And then we take hundreds of them and combine them to have one combined single mode output. And that's how we reach the more than 100 kilowatt single mode output in our product. And we monitor the output, and with some fast real-time electronics, we control the relative phases of these lasers to allow us to do this coherent beam combining. So first of all, here is the ability to get to extreme high power with a single mode output. But the other part of the technology is what's called optical phased array. An optical phased array, it means that we take all these lasers and they emit light in parallel, and there is an overlap of their output. Now, where there is an overlap, there is interaction between the different lasers, and you get constructive and destructive interference. And in some points, you get constructive interference where all the energy is focused. In other places where there was light before from each individual laser, they actually cancel one another out, and you get darkness. So this is very well-known phenomena. It's basically the diffraction pattern or the diffraction grating, that in some places you have constructive interference, in some places you have destructive interference. But if in parallel we can actually control the relative phases of these lasers, we can make this beam move, change position, change shape, and change focus, all by just controlling the relative phases. Now, changing the phases is just an electronic thing. We can do it at tens of megahertz. There's no moving parts. It's just an electro-optical device, a lithium niobate device. So it's extremely high reliability, very, very fast. And we can get to these very, very high powers of tens or hundreds of kilowatts with this control. So the result is what we call the dynamic beam. And what you see here on the right are different shapes that we create. This is a 14 kilowatt laser. And I'm stopping this for a second just to tell you that the width of this line is roughly 50 micron, and the whole area is about 350 to 400 micron. And inside this area, basically this would be the area of the melt pool, we can move the beam and do different beam shapes to control the melt pool. Now this whole thing can be made larger or smaller according to the focal length of the focusing lens, the focal distance of the focusing lens that we're using. So like I said, this is a line of 50 micron with an area of roughly 400 micron, but the whole thing can be larger or smaller by just changing a lens. And the point is that we can do beam shaping, sequencing, and so on, but all at very high power, very, very fast, and very reliable. I think it was perfect, the order of the presentations that we just heard, how with Galvo you can do dynamic beam shaping and how important it is, but it has the limitations of how much power you can put on the Galvo and how fast it can move. And by us, it can move very, very fast at very high reliability, at very high power. Now, to design these beam shapes, we have this very, very simple software that we provide to the customers, where basically you have this grid and you go with your mouse and you just click wherever you want energy. So you see, you just go with the mouse and you click, and right away in the window on the right, you can see a simulation of what the beam is going to look like. And you also, when you go over it with your mouse, you can actually see the cross section and know exactly how much energy and what is the energy distribution inside the shape that you designed. And then you can just go ahead and change the design and immediately see what would be the energy distribution inside this beam. By the way, you can click, if you click one time, you get some amount of energy. If you click twice or 3 times or 4 times, you get more and more energy. So you can really do any type of energy distribution inside this region. So once you have the shape that you want, you just save it to the computer, you upload it, and you do an experiment. And of course, it's clear that you can see different behavior of the weld cross-section when you use different beams. And from this, you can get the feedback and go ahead and change the beam again and continue this process. And very, very easily, very, very quickly, you can achieve the optimal process that is required. So just a few pictures. So this is a fast camera from our application lab. And you can see that on the left, with one beam shape, you get a very unstable keyhole. You can see a lot of sputter here. Whereas if you look on the right-hand side, you see a very, very stable keyhole with this other beam shape. Another important element is that when we design a beam shape, so for example, if we decide that a beam shape of 2 point that is perpendicular to the propagation direction, this is the beam shape that we want to use. When we go around and create a part, the orientation of the beam shape always has to be perpendicular to the propagation direction. So by us, it's very, very simple because we just electro-optically control any shape that we want, and we can make sure that all the time the orientation of the shape is also in the right orientation compared to the propagation direction. Now these shapes and all the parameters of the beam can be controlled in real time by the whatever CNC machine it is. So here we're showing a galvo scanner that is controlling in real time our dynamic beam. So what you can see on the left, you can see here the beam shapes change from 1 point to a spiral, and this is done in real time by the galvo scanner. So you can see the galvo scanner making this square, and in real time controlling the beam shape. So every facet of the square has a different shape. This is a slow motion. It actually works much faster than this. And you can see on the right, so the top and bottom lines are with 1 point, and the 2 sides are with a spiral. And of course, you get a different cross section, or this is a top view, but a different weld with a spiral compared to a single point. Another very important feature is the ability to control the speed of this motion. Like Patrick mentioned, we can do, let's say, a spiral like that. We can move it in 10 megahertz or 20 megahertz to make this beam. So the interaction with every point is in the nanosecond area, or we can move it much slower, as slow as required, and then you can actually have some kind of dynamic motion of the keyhole in the melt pool, and perhaps have some dynamic of the fluid or stabilize the keyhole or so on. And of course, the interaction with the material is completely different. You can see here one shape, all the parameters are the same feed rate, same power, same beam shape. The only difference is the frequency of the beam shape, or the speed by which we move the beam, and the interaction with the material is completely different. The next level is actually taking several different shapes and working them in sequence. So we can save some shape, let's say this hourglass shape with some frequency, all the parameters are set, and we save it on the computer. Then we take another shape and we save it on the computer, and we can actually do 256 different shapes and save them and create a sequence. And the sequence I mean is that you save and you say, I want the first beam shape for 1 millisecond, and then I want the next beam shape for 10 microseconds, and then the next one for 100 milliseconds or whatever, and then automatically it goes from one to the other. What you can do with it is all kinds of interesting things. So for example, if we have here a shape that has a fixed part and a moving part, okay, so again, there are many different applications and many reasons to do different sequences like that, but just to give you an idea of what can be done, of having some kind of a fixed element of the beam with a moving element of the beam, this is all done very, very easily. Another interesting application is drilling through a multi-layer material. So for example, if you have here a metal that is coated with some coating, let's say ceramic coating, and they are glued together, and you want to drill through this. So of course, the ceramic has completely different properties than the metal. So you want to optimize a beam shape that is different for the ceramic than it is for the metal. And in the interface, many times there are cracks and separations that is created when you drill through it. So maybe you want to have a different beam shape when you go through the interface to protect this interface, sensitive interface region, to avoid these cracks and separation. So by us, it's very easy. You just design a sequence. You do a test and see how long it takes to penetrate each layer. So let's say it takes 150 milliseconds to go through the one. Of course, this is a much smaller numbers, yes, but let's say you go 2 milliseconds to penetrate one layer, 1 microsecond to penetrate the interface, and another few milliseconds to penetrate the metal. For each one, you design the right beam shape, and you just drill right through with the changing shapes. Another important property of our laser is the fact that it's single mode, which means that the depth of focus is very large. So inherently, when you compare a multi-mode, in the blue you see a multi-mode laser, compared to a single mode laser, the depth of focus is already much higher with a single mode laser. But in addition to the inherent depth of focus, we can actually control the focal point to achieve even larger depth of focus. And this can be done, again, just like we can move the beam in the XY, we can also move it in the Z. And again, this can be done at 10 megahertz over a range of a few millimeters. And here we see some results. So in the chart, you see on the left, you see a cross-section of one shape, and on the right, you see cross-section of a different shape of a spiral, where the top line is with a fixed focus and the bottom line is with focus steering. And of course, again, just like was just presented in the previous presentation, you get a much smoother and no druce, smoother cross-section and no druce at the bottom when you actually do the focus steering. But again, with our laser compared to a Galvo, it can be done at any power, at any speed, and very high reliability. So it opens up a whole new options. So this was like the core basic technology, and now just a few applications that we're doing today for automotive, aerospace, and just general steel manufacturing. So this is all done in our application lab. What you see here is the optical path. Basically, the laser is here on the left, and the beam goes. There's a folding mirror here or a scanner. We can put here either a fixed mirror to go to the really high power, or a Galvo scanner that can go up to 4 kilowatts. And here at the bottom, we have an XY table, and this is where we do the experiment. So there's a lot of fundamental research that we do for ourselves to understand the parameters. There's a lot of proof of concept that we do for industrial companies. And of course, we do a lot of collaboration with academia. So a few examples. So this is an example that we actually published together with Valeo and Ayman. And the idea is to take a battery cooler and that is manufactured today with brazing and replace it with laser welding. So we got samples. This part represents the cooler, and we developed a very fast and very good weld with good geometry, good strength, no porous, no sputter, at very high speed. You can see a longitudinal cross-section to see how stable it is. And of course, we did the leak test, and it's leak-free. So this is one example of the dynamic beam being able to develop a process which is very difficult. I think most of you probably know how difficult it is. So then we wanted to try to see the influence of this sequence that I mentioned. So we created here a sequence. This is a work that was done together with Bosch and IFSW. We created here a sequence where we start with single point, and then we go to 3 points, and the distance between the 3 points grows, becomes larger, and then becomes smaller again. So basically, we increase and decrease the whole beam size. So this is done in a sequence that we pre-program it in advance, and we change the sequence frequency, how fast it happens. And we did it with a feed rate of 500 millimeters per second. Okay, and what you can see here clearly is that when you have a slow frequency, you have the periodicity here, and as the frequency goes up, the periodicity is increased, right? So this is you can actually see with your eyes the sequence, how it happens. Now, this was really done in preparation for copper, or just before to say is that we actually, everything we do, we take pictures with a fast camera. So this is a nice trick that was done here by Bosch. They overlaid all the frames in the fast camera, and you can actually see the 3 points. We did both this direction and this direction. You can actually see it in the video, which is low resolution, but when you integrate over many frames, you can actually see the beam shape on the material itself. So anyway, this was really done for copper to see how we can optimize copper welding. And really, again, you can see by changing the frequency of the sequence, you can see different behavior in the copper. And the idea was to see how it behaves and try to get a very good fast and deep penetration weld in the copper. So this is still work that's being done. It's clear that the different beam parameters affect the process and the quality of the weld. We still have to do further work to develop the best results for the copper. Another thing that we investigated is welding of dissimilar materials. So for example, we have here aluminum welded to copper, and here we have aluminum welded to stainless steel. And clearly you can see that by changing the beam shape, you get different results in the beam. You can control both the geometry and the amount of intermetallic mixing between the two dissimilar materials. Another very important field that we see as a substantial advantage for our laser is deep penetration welding, because we can provide extreme high power at single mode, so you can have a very nice deep penetration welding. But again, as probably many of you know, that when you do that, you get a lot of porosity. But with the beam shape, and with some dynamics, we can actually get rid of porosity. So here are just a few examples of deep penetration welding in stainless steel and in aluminum. And we saw that we can get very deep penetration welding, but sometimes you get porosity. And by introducing some dynamics to the beam, you lose a little bit of the penetration depth, but you get a very, very good weld. Now we can also increase the power. I mean, this was done with our standard OPA6 with a maximum of 10 kilowatt, but we have today 28 kilowatt and 100 kilowatt laser. And we anticipate that with the higher power, you can get really, really high speed, very high quality, deep penetration welding, both in aluminum and steel. So, without showing more details, just to say other things that are happening currently in our application lab. So it's cutting of carbon fiber reinforced polymer, CFRP, welding of amorphous materials, drilling of multi-layer materials, welding coated materials, and removal of amyl coating. This is actually, again, like Patrick mentioned, our laser can start overlapping with pulsed lasers. When you want to work like a pulsed laser, because we have such high power density and move so fast, it starts working like a pulsed laser. So some application that today is being used with a pulsed laser, we can do with our laser, and then you can use the same laser to do different processing, like here, for example, to remove the coating and then do the welding. So things that we want to do in the future, as we mentioned, our laser can do many, many things, but if you actually want to do in real time optimization of the process, so we're thinking about taking some monitoring systems, cameras, thermal cameras, measuring of the depth of the keyhole and so on, and in real time changing the beam parameters to optimize the process in real time. The other very important thing is simulation, because it's so complex, these processes, and there are so many options that you really want to know what you're doing. So this is an example, a very nice example that from Professor Andreas Otto from TU Wayne University, where he simulated our beam, basically a ring here that can move around at different frequencies. You see, this is at 2.6 kilohertz, and this is at 260 kilohertz. And you see right away how different the behavior of the keyhole and the melt pool is, where you see actually a lot of sputter created on the left, and you see very, very nice open keyhole on the right. So this is a very important tool. It has to be much more developed to be more readily available and useful, but this is definitely another thing we want to do in the future. So to summarize my last slide, it's clear that the dynamic beam strongly influences every process. Civan's dynamic beam has many parameters that can control the process that really are not available today by any other method. But each application requires optimization and process development, and we need deep understanding and future study for each process that has to be developed. And this, of course, is something we want to do with IWS, together with them in the lasers that they have over there and with the lasers that we have over here. So thank you very much.
Thank you, Eyal, for your nice presentation and your insights in first applications and potential applications. There are some questions here in the chat, and I think we shall start actually with the questions. And I think the most questions you might be able to answer, and there are some questions maybe Eleanor is able to answer. So the first question is, could you state on the cost per kilowatt of the CBC system? Eyal.
Yes, so the cost per kilowatt is changes a lot. Basically, the higher the power, the lower the cost per kilowatt, because our laser is a complex laser, so there is some minimum threshold that we have a built-in cost. So it's almost in any power, whether we do 8 kilowatts or we do 30 kilowatts, it's the same laser basically. We just have a little bit more power in each one of the lasers. So again, the higher the power, the better the cost. I think that in higher than 10 kilowatts, we're already very cost competitive. I don't want to give real numbers here, but I can say that higher than 10 kilowatts, I think we're closely competitive with the market. But of course, you get a completely different product. What you get is a single mode dynamic beam compared to a multi-mode laser that's available by others.
Okay, Eyal, thank you. The next question is, how many channels are needed to reach 14 kilowatts?
So we use 32 channels, but not because we need it for the power, but we want to have a dynamic beam. I mean, in order to have the dynamics of the beam, we always use as a minimum 32 channels. That actually relates well to what I just said before, that even if somebody would ask for just 4 kilowatt laser, we will still use 32 amplifiers for the dynamic beam, and that's why it's more expensive at the lower powers.
Okay. Eyal, the next question is concerning the lifetime degradation rate for this laser, for the 14 kilowatt laser.
So this is it's a fiber laser, and we ran some of these lasers for thousands of hours. Every laser runs by us for many tens of hours, just as we assess before we ship it out. But when we did the qualification, we ran it for more than 1,000 hours. We also have lasers that are ready for 3 years by customers, and we don't see any significant degradations. Again, it's based on fiber laser technology, and in fact, we are reaching the very high power, but each one of the lasers is only 1 kilowatt. So it adds to the reliability and lifetime of the system.
Okay, so the next question is about the modulation. So can you modulate only the phase of the megahertz frequency or also the laser power of every module?
Okay, so we, at this high frequency of megahertz, we can only modulate the phase. So the phase can be modulated in this high frequency, and if somebody wants, we can move the beam to the side, so to speak, and do all kinds of pulsing and stuff like that, but we don't turn the laser off. The intensity modulation, by actually turning the laser on and off, is done at more of a kilohertz regime.
Okay, so then, and the next question, is a dynamic beam shaping technology suitable for powder bed fusion additive manufacturing of titanium? What are the opportunities and challenges? Actually, I'm trying to answer these questions. In general, yes, it shall be possible and we will test it, but not at the first run. So we will carry out basic trials. Mainly we will start with welding, and the next step actually will be testing, on powder melting. And for sure, we do have titanium in mind. If I talk about opportunities and challenges, actually, we can talk about ours. So the answer is general yes. Maybe Elena Lopez. Elena?
Yes, sure. Thank you, Eddie. Yeah, sure. Thank you, Eddie, for this question. That's great that you're taking part today in the discussion. Yeah, concerning the opportunities and challenges, as I'm going to describe in my presentation, we will be focusing first of all on the laser metal deposition setups because we are much flexible to change things there. We don't have the rigidness of a commercial system like LPBF usually are. And we will be making first experiences with the use of the dynamic beam shaping of Civan. So the procedure will be to study LMD and then focus on a customized LPBF setup and make some experiments there as well. So the flexibility of LMD also concerning titanium. No? I can imagine you're also thinking about bigger parts made of titanium, like we are processing up to 3 meters, and there the high power and the high productivity are really of interest while processing titanium. And while working on powder bed, we are more limited to use the whole potential of high power laser systems. So I can confirm the views of Andreas. We will be also taking a look at this, but we will be focusing in the next term on LMD systems.
So the next, thank you, Elena. The next question is your dynamic beam shaping with multi-kilowatt lasers already used in industrial serial applications? If yes, what are the applications? I'm not quite sure what is meant. So if it concerns the Civan technology, actually, I'm asking Eyal if it concerns actually the conventional beam shaping technology based on galvanometer scanners, I can say yes, there are applications. There is one laser cutting machine manufacturers who offers a machine which has the dynamic beam shaping as an option. So obviously, and it improves actually the cutting process as explained by Patrick Herwig. And in the case of welding, yes, there are also applications. And there's one application we as Fraunhofer IWS, we are working on, and it's welding of cast aluminum parts. Dirk, are you saying, or do you want to say some sentences towards this application?
Yeah, I can just tell you this is under investigation using the Civan laser right now, and for 2D beam shaping we already have some solution available for this topic. So in that case we extend it to the new laser source.
So in Eyal actually, so how about the Civan laser used already for
we have
industrial
some laser
applications?
Yeah, so there are a few lasers placed by some customers, but I don't think it's still in serial production by them. It's more of a prototype that they are testing the technology. I don't think that by any of them it's already in serial production. But it's in different fields of material processing.
Okay, so thank you. I have to stop now asking and answering questions, because we need to be actually on track. And now I'm trying to share my desk, my monitor actually, because I will talk about the first results, that we have achieved in our lab. And I will start with a lab tour, which we have recorded quite recently. So welcome to our novel Civan lab. Here on the left-hand side, we have the operator's place. This is the place where the operator is running the laser if the laser is turned on. As next, I show you active laser protection walls. The function is to avoid a direct exposure of the operator to the laser radiation once the laser is used for experiments. Here we have the laser cabinet. The laser cabinet contains the single fiber lasers. We have 32 single fiber lasers. Each laser has a power level of 500 watts. These 32 single fiber lasers will be guided by 32 single fibers which are within this hose here to the beam combining box. The beam combining box actually is the box which is providing the technology of the coherent beam combining. And this coherent beam combining enables the fast change of the power distributions. And this is what we are looking for, and that's why we do have the laser here in this lab. Once these 32 single fiber lasers are combined, a raw beam will leave the combining box by this window here, by this outlet window. The shape actually is square shaped, and it has a dimensions of 32 by 32 millimeters. The raw beam is next will be focused either by a focusing lens or by a beam bending mirror, which is at the same time a focusing mirror. The focusing length has right now a focal length of 1.5 meter. And if we don't use the focusings and instead of this focal lens focusing mirror, we have two focusing mirrors. One has a length of 1 meter, another one of 750 millimeters. So, and here behind the beam bending, because we can remove here this beam bending unit so that we have the raw beam hitting this plate here, and this device is for an exact power measurement. It's a power meter in order to measure the power. Here we have our experimental setup. At the moment, in our first step, we are doing a beam characterization. As I said, we are measuring the power for sure, but most interesting is the power distribution, because that's why we do have the laser here. Coherent beam combining will provide us unique opportunities to change the power distribution within the focus very fast. Almost each different shape is possible, and in order to characterize this, we are using this so-called microspot monitor. The focal position is about in this level here, and the focal size is, the diameter actually of the focal is about 0.5 millimeters. Once we have characterized the beam, we will start with our first experiments. We will start with bead-on-plate experiments, bead-on-plate trials on metal plate, aluminum, steel. These are the first metals where we start on. The next trials will be welding trials, and as next we will carry out trials on melting powder and wire by means of the changing modified power distribution, and as a last step we will conduct laser cutting trials. In order to conduct the experiments, we do have here a stage, an XY stage, where we can move the samples and the parts in XY directions, and in order to move the focal position in Z position, we can move here the whole stage upwards and downwards. The laser can change the power distribution in X and Y directions very quickly, but this is not enough. At the same time, the laser is able to change or to oscillate the focal position by means of coherent beam combining very fast in a range of several millimeters with a frequency in the range of megahertz.
This shows you our colleague, Michael Lewinsky. He was carrying out the beam characterization. So on the next slide, you can see our experimental setup. So we are using here a focusing lens to focus the laser. Then we have here a beam bending mirror, and right now the focal length is 1.5 meters. We have also the option to use, instead of a plain bending mirror, the option to use a focusing mirror with a focal length of 1 meter. And then we're using here the microspot monitor by Primus. So your thought is on the right hand side, again, you see the machine, the system, and the framework here. And you can see here actually on this arrow actually where the laser beam is hitting the measuring device. So I have, for you, I have some examples actually, what kind of shapes we have here generated, and what actually we have measured. So on the left hand side, actually, you can see the way how the shapes are generated. And if you want to have, for instance, here a kind of a pillow shape, you have to set here along this circle, you know, several points. And if you do so, you get this calculated beam shape. And for us, quite interesting, most interesting was, what does it look like, you know, in the real world? And what does it look like, the power distribution, if we're using our measuring equipment? And this is what you can see here on the right hand side. So this is actually showing you what we got, you know, once we have programmed this kind of, we call it pillow. So what we got in reality is very close to this pillow, but you have to keep in mind that the measuring method actually is even interfering, you know, with the laser. And it has something to do with the repetition rate of this shape and of this power profile, which is interfering actually with the repetition rate of the measuring device. So on the next slide, I have another example. We have programmed a so-called horseshoe. And here on the left-hand side, you can see
what the calculation is saying. And on the right hand side, you can see what we have got after passing the focusing lens in the focus position. So, and the distance between the two peaks, which are programmed in the horseshoe, are 60 microns. Once we have characterized the power distribution, we got a good feeling of what we are expecting. We have also done the first trials with just a peak in the middle. And this is seen here. So this is programmed, and this is what we got. And just quite recently, we have removed the microspot monitor from the XY table, and we put a piece of mild steel underneath the laser, and we just did a linear bead on plate welding of mild steel with several speeds. What you can see here in this short video is done with a speed of 10 meters per minute and with a power level of 5 kilowatt as a very first trial, very first usage of the laser in our lab for material processing. So I will run this video. So I just will it run again. And in order to investigate what we have welded here, we have just done two cross sections. On the left hand side, you see a cross section of this bead on plate weld carried out with a speed of 10 meters per minute. We are reaching penetration depth of almost 2 millimeters. And on the right hand side, you can see cross section done with a welding speed of 1 meter per minute and 5 kW, and we can reach a penetration depth of more than 4 millimeters per minute. Again, these are very first results, and I'm showing these results to you in order to demonstrate, that the laser is ready to be used in our lab. So the question is, what are the next steps? What are the next things we have in mind? We will do some basic research to have a better understanding, a detailed understanding of what is going on, what is achievable with a certain beam profile, and how can we affect the melting pool. That's why we will do basic studies of the effect of different and changing beam profiles on the weld seam shape. We will do the same, actually, basic studies of the effect of the fast oscillating opportunity. So we can, Eyal Schegel has mentioned that we have the opportunity to oscillate the focus along the penetration depth or along the material thickness. And what kind of effect has this on the weld seam shape? The next step is to transfer these results to a real welding process of thin and thick stainless steel, aluminum and copper. The next topic, we will look very close, and this was already questioned, or this was already asked. So a basic studies of the effect, we will study the effect of different and changing beam profiles on metal powder welding. And we will do the same or similar things on the effect of different and fast changing beam profiles on wire welding. And last but not least, we will carry out basic studies investigating the effect of beam profiles and oscillating focus on the performance in the case of laser cutting. So this was my presentation. The first insights to the lab work, which we have done here during the last weeks. And I'm very sure that the next exciting results will follow. And the next results will be presented within a joint presentation with Civan and Eyal Schegel within our laser symposium, which will take place in beginning of December of this year. Thank you very much. And there might be a very little time for questions.
Yes, I will ask the question. There are two questions in the chat. As first, sorry for the video, yeah, but I think there was a problem with bandwidth, but I think it works. The first question I could answer, yeah, yes, we use the interference of all lasers, yeah. Of course, you can switch off also some of the lasers, but this will decrease the freedom of the shape we will achieve. And also it will reduce the maximum laser power. And I think this is also the near question answer to the third question. Yes, the pillow was mentioned with the frequency, but it's, as you also use the CW lasers, you can also use them with a frequency, but with a laser on time of 100%. Yeah, so it's the nature of the laser. And we have a lot of possibilities to operate them. Yeah, we can also make a single dot which is moving in this pillow shape. But for the first tests, we start with this kind of a static pillow shape, yeah, and not internal moving pillow shape, yeah. And regarding the resolution and dots, I think we start with dynamic beam shaping with only moving a single beam, yeah. Now we have 32 beams which are working in the interference together. So we had a lot of possibilities. And maybe Alex can add to my answer, yeah?
Yeah, so maybe I can just say that
yes.
The resolution is very, very high. I mean, you can reach a resolution of a fraction of the beam diameter. So, I mean, you can step every few microns if you want. It's just the matter of designing what is reasonable for the process. But whatever resolution, basically, you can step in jumps of 1 micron if you want. So it's all available. Just a matter of design.
Just a last comment from my side. We are just at the beginning. So even, the scientists and engineers here at Fraunhofer IWS, we are just to learn what kind of opportunities the laser will give us. So, and to be honest, it's not easy because it's sort of overwhelming, even to us. So, and we will actually gain some experiences during the next weeks and months. And I'm sure we will have actually the opportunity to use this very, very strong tool. So the laser actually provides opportunities that we have never seen before. So with oscillating and fast moving mirrors, we got decent results, but we were limited, in many terms to say this. However, in order to be in time, I would like to ask Dr. Elena Lopez to start with her presentation about the first public funded project, which is about on-the-fly laser beam shaping of laser metal deposition of crack-sensitive aluminum and titanium alloys. Elena, please.
Yeah, thank you, Andreas, for the introduction. I hope my presentation is visible for all of you.
Yes, it is.
Perfect. As mentioned, we are happy to inform about the first funded project within the frame of the MERANET program concerning the application of these laser sources to the field of additive manufacturing. So, as it has been mentioned before, especially during the question time, we do have the possibility to adapt these systems to a wide range of technologies at the Additive Manufacturing Center in Dresden concerning additive manufacturing. Obviously, we have been thinking about the introduction in different systems. We are also exploring the possibilities to work on the laser powder bed fusion sector. But as mentioned before, due to our long experience, or more than 30 years, concerning the system development in LMD technology, laser metal deposition for powder and wire, it seems the more reasonable to start focusing there, also for the high power system, and then moving later on to the more complex due to the commercial system field of LPBF. So the first project will be focusing on the technology laser metal deposition. As mentioned, we were successful last year to submit a transnational project on the field of additive manufacturing within the mRNet call, which enables the participation also of external European countries. And we were focusing in this time on the material research for additive manufacturing. So we were successful on the sixth topic of this call. So the main goal for this so-called SHAPE AM project, on the fly laser beam shaping for laser metal deposition of crack-sensitive aluminum and titanium alloys, was obviously to scope the possibilities to bring this laser source that Andreas has shown at the lab to be able to process crack critical materials like aluminum and titanium for additive manufacturing. So there are a lot of questions still open, like the adoption of this system for the field of additive manufacturing, for the handling of powder, like many of you obviously would know as a challenge while talking about additive manufacturing, but also scoping the advantages of processing wire with these systems that opens the possibility to skip the whole handling, and it's a much cleaner process while working with this system. So we will be scoping both directions and putting or making this system fit together with other partners for an industrial setup for LMD in additive manufacturing. The sub-goals, I would say, as we have been hearing in the different presentations today, obviously, is using this innovative laser beam shaping to enhance the control of the melt pool for additive manufacturing. It means to enhance the control of shape, of size, dynamics, and oxidation issues related to the melt pool. Reduce cracking, which is an issue, obviously not only for aluminum and titanium alloys, but also for high temperature alloys like nickel-based superalloys and so on, that we will be focusing later on. To reduce the surface roughness by tuning up the laser intensity that is feasible with the beam shaping. Control distortion, also again by tuning these different laser intensities, which is an issue obviously while moving to macro parts in additive manufacturing. And out of the scope maybe of this project to follow up the approaches of doing AM of the similar materials. So use this system also to combine materials, multi-material AM, and enhance processing critical and even completely new materials. As we know also from the material development in the field of additive manufacturing, that by using LMD, we can aim to in situ alloying to create even new alloys in situ. And this new technology may help us also to enhance the processing. The consortium is made or consists of Fraunhofer IWS, as mentioned, in the role of the coordinator and improving the available system technology with wire and powder, carry out process development in that field, and support the colleagues working at the technology field of Andreas Wetzig on the field of simulation with empirical data, and then carry out together with our materials experts, material analysis and testing. And obviously at the end of the day, at the end of the project, we have a demonstrator, for instance, in the field of aerospace or space based on aluminum and titanium alloys. Civan will scope the possibility of using their beam shaping technology, the beam laser sources for the use in additive manufacturing, and will support us defining parameters, support us with the programming, obviously, and this temperature or this 3D temperature tailoring. And will test also with us these new crack sensitive alloys. So we schedule some alloys that are now in the community being quite relevant, like scam alloys or A82219. Those of you working for aerospace would know these alloys, and titanium 64 as reference. And in the end, an Israel company, Kotlia Engineering, with experience on machine developing, machine design, they would aim to especially implement the wire LMD system technology to their system combined with the beam technology, beam shaping technology of Civan. This is the plan structure of the project. Obviously, a lot of work in parallel for the different alloys. We will be starting, or we have started the project in July at the lab that Andreas showed you before. So the first steps will be obviously implementing the environment for additive manufacturing to this lab, and start doing some reference experiments with powder, and administrate as well material for the simulation paths that we are going to follow in this project. So the objectives, as mentioned, are the definition of optimal beam shapes at the end of the project for powder and wire LMD, the simulation of new beam shapes and beam reflection rotors for an optimal powder and wire LMD process, the design of a prototype together with our industrial partners that is relevant for the industrial application, and then obviously, as in any project, European project, on material development, production of these specimens, and characterizing destructive and non-destructive these specimens for the application. And so we hope at the end of the day to have a system, a machine, at least a prototype, able to be used in industrial applications together with Civan and Kotlia, and to have demonstrated this technology, this control of cracking, this control of distortion, and tailored material properties with these alloys on a real interesting industrial demonstrator, just to summarize, let's say, the scopes. So I wanted just to show you, or to share with you, some of the obviously also struggles and challenges we are facing while using this system for the first time for additive manufacturing. Andreas already showed very well the actual situation at the lab. And the situation, as mentioned, is that the beam exceeds the collimated shaping unit, and we have a beam shaping figure only defining focus, and we need to make this system suitable for the additive manufacturing process. You know that we will be starting with the reference process with powder. So we need the powder handling, at least in a rudimentary approach, and we need the exhaust system to work safely. So we will be implementing the exhaust system there. We have at the moment no synchronization of the laser and the wire feeder or XY table, but we will implement this, and also work with, at the very beginning, with a manual set adjustment at the moment. And let's see, in the next months of the project, we have just started how to make this automatically as in other available LMD systems. So the next steps is to ensure the process enclosure. We need obviously beam shielding, and to avoid also reactions and to avoid oxidation. We will construct the nozzle holder. The nozzle technology, the coax nozzle technology, comes or is being made in-house at IWS, so we have very valuable experience already on the construction and adoption of those nozzles, and then integrate the exhaust system as mentioned. And the first planned experiments will be focusing on the buildup of cylindrical geometries with the beam shaping, with this manual set adjustment as mentioned, and diffuse the powder sprays to generate or make use of the laser figure that is visible with this system. So we will start with some standard materials and then move to the project materials. And then in the meantime, parallel to these activities, the colleagues with wide experience on simulation will already feed the micro models and macro models with already available data on the film L&D from IWS to develop and implement this two-based model system, and do a model calibration finally to compare them with empirical work, let's say. So I'm not an expert on simulation. We have fortunately the support there of the colleagues working with Andreas, but there are some challenges, as you may know, also while working with these simulation processes and also from the process side, which is are listed here, let's say, and it is to follow the phase change, to modeling the Marangoni effect, which is well known for LMD processes, and especially also challenging for aluminum, as you may know, for the concerning the evaporation side effects also of some elements that are being taking part there. So we will study the surface tension viscosity and empirical constants, and then the free surface issue will be also taken into consideration. I mentioned we can modify also the shape and the size of the deposition track, and we'll focus on this also for the feedback from the simulation. And finally, use all of these facts on the model calibration. So this is from my side. This is all. As you have noticed, the project is quite young, and we are very happy to work in the upcoming years on this technology, and we'll be happy to share with you in the upcoming conferences, hopefully for ISAM, or if not, in the upcoming ICALIO conferences and so on, first results on this technology for additive manufacturing. Thank you for your attention.
Thank you, Eleanor. There is one question, and I think there's time to answer this question. It's related to your presentation. What are the expected advantages of the Civan laser technology when working with crack-sensitive materials?
Okay, so as mentioned in the first slides, we expect here a different temperature regime, or we can also do through the modulation of the laser intensity, we can expect different temperatures, and we can expect also a regulation of the material properties locally of those crack-sensitive materials. So in the end, what we are going to aim for is to control the cracking, or to avoid the cracking by having this different distribution of intensities. This is an issue on innovative aluminum alloys, on titanium as well. As I mentioned, on crack-sensitive materials, high-temperature materials, like for instance nickel superalloys, also nickel aluminide based alloys. So it is actually a big or a big spectrum of materials that can be used here to tune the material properties. As I also mentioned, we do think that by controlling or enhancing the control of the melt pool, we will be able to control as well the distortion issue, that it's still an issue on additive, especially for bigger parts. And as well, in the field of aluminum and titanium, avoid some kind of oxidation that at the time are also controllable under the use of gas chambers, or localized gas chamber nozzles like the coaxial technology.
Thank you, Eleanor. Due to the time frame, actually, I would like to introduce and to ask our last speaker, Mr. Eric Punzel from BBW Lasertechnik in Bavaria. I would like to ask him to take over and to start the presentation about laser welding of hard-to-weld aluminum alloys within the new CBC beam shaping technology. So it's your turn, Mr. Punzel.
Thank you for the introduction. You can hear me very well?
Yes, so we can see the presentation and we can hear you.
Wonderful. Okay, my name is Eric Punzel and I represent today my company, the BBW Lasertechnik, as well as the research project WeldShape, which is funded by the Pulsate Corporation. So, a moment. So, shortly something about my company. We were founded 23 years ago near Rosenheim in Bavaria. And since then, we are a poor job shopper for laser material processing, like laser welding, cutting, drilling, marking, and USP processing. Currently, we have over 160 staff members and around 45 laser systems. 2/3 of them are used for laser welding. And a significant part of the laser systems are also built in-house. We have an internal construction department for fixtures and a quality assurance department, including a metallographic laboratory. And of course, the process development team is mentioned, where I'm part of it since 3 years now. We accompany the feasibility studies and the process development, beginning with new prototype components and adjusting the laser processes onto new parts coming into our company. So compared to a university or an institute, our work may mainly focus on production improvement, but we also take part in national and international R&D projects, which is the reason why I can present you something today. So far, something about the company. Let's go now into the main topic, or there's also Civan, part of the Pulsate project, but I think they have introduced them already, or Eyal has introduced his company very well, so I don't need to add more information here. To mention is also the Fraunhofer IWS. They will assist us in the duration of this WeldShape project. And to say the project has just started 2 weeks ago, so we are at the very beginning. So we need to start with some basics. It is well known that laser or welding in general is never a 100% clean process, and the weldability depends also on the used material. There are alloy. Let's talk for today about aluminum alloys. They have a hot crack danger, as well as other alloys with a high pore formation. There are, of course, different strategies against these welding defects existing, mainly with some kind of beam shaping. So this topic is nothing completely new, but all these strategies are very limited in its area. So I want to shortly present 2 existing strategies already very well established in the industry. So one strategy against welding defects is wobble welding. We have 2 mirrors inside the scanner. The combined movement results in a 2-dimensional, very dynamic movement. So for example, by using a circular oscillation geometry, the laser beam passes over the same position several times and interact with possible gas bubbles inside of the melt, which leads to degassing. It is a great technology, but the acceleration and the speed is limited by the mirror masses. So state of the art is maximum 4 to 6 kilohertz of wobble frequency is possible with this system. Therefore, wobble welding in combination with high-speed welding is until now hardly possible. Also mentioned today, investigations with pressure cast aluminum, which have a very high base porosity, suggest a much higher necessary frequency. So this is another interesting investigation topic, not only for us. Another existing strategy is the usage of superimposed intensity distribution realized by a 2-in-1 fiber. There are different comparable technologies like Brightline from Trumpf or AMB, IPG, iron coherent. So around the core fiber is a ring fiber, and the additional laser intensity in the ring leads to a stabilization during welding and less sputter. However, also here we are limited in the form of the superimposed beam. So only concentrical superimposed intensity distribution is possible, nothing else. And we are also limited in the speed of a change in the intensity distribution. So for example, multi-spot beam would here be very interesting for the evaluation of possible hot crack danger degrees. So we have now seen the limitations of existing technologies. They are available, but can only address specific problems in its limited way. We have already seen today that Civan has now developed a unique technology or use a unique technology in the high power application called coherent beam combining. And BBW has always been early adopters of new laser technology. For example, we were one of the first using the new fiber lasers. We used very early scanner technology. And now we consider the Civan technology with its dynamic beam shaping to again be a possible game changer for the laser as a tool in material processing. So that was the reason that we made the decision to invest in this technology. So this technology, we have already seen it, addresses all these limitations of existing strategies. We could do wobble frequencies in the megahertz range, any shape of multi-spot or superimposed intensity distribution, and even beam shaping and Z-axis. So our experiment consists of two main topics. As well as the IWS, we want to build up a laser machine with the Civan system. In contrast to it, this machine will contain a scanner optic for the realization of short and remote high-speed welds. And what I know is that we will be the very first to combine a scanner together with the Civan system. The interface should also be industrial ready for future series applications. This is very important for us because we are a job shopper and we earn our money with using laser systems for our applications. Second, when the machine is working and the general functionality is proven, we want to investigate some of the already called approaches, beginning with hard-to-weld aluminum alloys. You see here a really early first concept of the laser system. This concept has already changed, but it's still work in progress, so I cannot show you anything new. Sorry about that. There are many more investigations possible, but within the limited timescale of the Pulsate project, we will concentrate onto the build-up of this demonstrator and first investigations with example hard-to-weld aluminum alloys. Of course, we are looking forward for more investigations and cooperations about this topic, coherent beam combining, together with Civan, with IWS, as well as with other possible partners. So this is all. I hope I gave a little insight into this just started project, and I'm now open for questions.
Thank you very much, Mr. Punzel. There are obviously no questions so far. Then I will take over with the last slide from my side. So the last slide is about the opportunities for industrial partners to use our joint lab in Dresden. So I have here some topics compiled. So first of all, our lab here in Dresden at Fraunhofer IWS is run jointly between us and Civan. So the laser is Civan's property, whereas the rest of the system and the lab is owned by us. In general, the lab is accessible for any industrial customer for its research. However, the experiments will be supported by Fraunhofer's staff, and if required, also Civan staff is available. Customers are allowed to use their own equipment like clamping devices, processing heads, and for instance, characterization tools. So these are just the conditions, and nevertheless, we will continue with the basic research and with the introduced public funded projects in order to learn what kind of capabilities the novel laser system will provide to the community of laser material processing. But however, at the same time, we would be glad here to have industrial customers from Germany, from Europe, and even from overseas to run their experiments. And again, everyone is invited actually to work here together with the Civan laser and our laser experts. So I'm just at the end of the online workshop, as there are a few minutes left, and Patrick, you have kept an eye on the chat. I'm asking you, are there any questions? Any general, Patrick, can you see any general questions, or actually I'm asking the audience to ask the question, but again, please use the chat function. Otherwise, it would be hard for me to sort the questions. But the easiest way is to use the chat function.
So Andreas, there are some questions. I think Elena answered one in the chat directly. Yeah. Up to now, I see no really important question. Yeah, I think there was a question regarding the scanning field which is used. It was a question from Blackbird, I think so. Yeah. Yeah, I think not really. Yeah.
Maybe one more comment from our side concerning the integration or the combination of the Civan laser with a scanner unit. So we have the same thing in mind, but so far we have decided to start actually with a simple setup, a setup using the laser as it is, and to study the effect of changing beam profiles and combining it with an X, Y, and Z system. And the next step, once we have gained first experiences, and if we have done the first real steps we have in mind, and we will combine our X, Y, and Z system with a galvo unit. Because as some of you may know, we are very experienced in using fast scanning technology to move the laser very fast along a certain contour in the case of welding, additive manufacturing, and also cutting and engraving. So, but in the first step, again, we decided actually to start with a simple X, Y, and Z system. Yes, there is a question here. Do you think the system will be flexible for cutting a wide range of thicknesses? So not only with high thickness material, but also thin in general, yes. But the general problem is how to provide the gas, which is used to reject the molten material from the cutting curves. So we have a solution in mind, but we cannot use just a cutting head as we do it for regular laser cutting. So this is a challenge if it comes to laser cutting using the Civan laser. Patrick, do you want to say some words?
Maybe
to the last question.
A remark from my side. I think in cutting of thin material, yeah, we have not really something to do, yeah, because the machine will limit us the performance of the machine, yeah. For 6 sheet, I think there will be a field, and as Andreas said, it's a really new cutting head concept, and we have some things in mind what we will test during our first investigation round in the lab.
Okay.
Regarding the fiber length of the transport fiber, we currently working with a free space laser, and if we are talking about combining by interference laser beams, I expect a fiber-based solution will be really hard. Yeah, I think from the point where we start to superpose these single lasers, we have to think about a free space solution.
Yeah, I can say that maybe for the 10 kilowatts, we can provide about 4 or 5 meters. So I totally agree that for large machines, it's a free space solution. But let's say to install it on a robot, you can install it and the whole head moves around. You have about 4 meters radius for movement. So it can also be moved to some extent.
Okay. I think the question is answered. So we have 5 minutes left.
So maybe I can also refer to one of the questions that was also Andreas, what you discussed about combining it with the Galva scanner and the XY table, to say that we already implemented a very, very simple protocol where our laser can be controlled by the scanner or the XY table or whatever CNC machine it's combined to change any shape and to change the orientation of the shape, and of course the power of the laser and on-off. So these 4 things, laser on-off, power, shape, and orientation, can be done in real time at a very simple protocol between our laser and the controlling machine. So whoever wants, of course, we will work with them to help implement it, but it's very, very simple. It works very well.
Okay. Again, there are some more questions. So if this is not the case, I will show you the very last slide from my side. But this is wrong. This was the chat function. So I wanted to show you kind of an advertisement. So the information of of the upcoming event of our laser symposium. So now it works. However, I show you this slide here. So we have the laser symposium at the beginning of December. It's an online event as well, and it combines the laser symposium with the ISAM, which is a conference about additive manufacturing technologies. And Eyal Shekel will give a presentation with the most recent results we have achieved up to then. And we would be happy to have many of you actually at this event as well. And again, thank you very much for listening. Thank you very much for raising questions. And we would be glad if we could have some of you here in our lab running experiments, first experiments, basing trials with the Civan laser, because only with applications from the real world, actually, the laser, will have a good market and a good chance. And everyone actually will learn from this application. So the laser manufacturer, the researchers and scientists here at IWS, and in particular, you as an industrial customer with certain requirements. Again, thank you very much. And I would like to see you, to hear you next time. And maybe we have a continuing workshop if we have more results. Again, thank you very much.
Thank you.